Hey, hello everyone. My name is Caroline Still. I am a program manager from the National Security Innovation Network, working with AFRL on this grand challenge. So welcome to the quantum imaging pitch competition. We have a very exciting run of show for you all today. We have the three semi-finalist teams from the University of Arizona, the University of Central Florida, and Purdue University here to share their exciting quantum solutions with you all. So I will be your moderator today. So you will see me throughout. Just for everyone's situational awareness, what is going to happen today is each team will be pitching for 10 minutes publicly, and then after the 10-minute public pitch, there will be a private Q&A session. We have an exciting round of speakers for you all during the breaks. And so we are very excited to have you all here today. So I am going to, without further ado, hand it over to Steve Zaraski from AFRL to introduce his team and speak a little bit about their challenge statement. So Steve, over to you.
All right, thank you, Caroline. First and foremost, I'd just like to thank everybody being online today, both from the government team, our support contractors, and our pitch presenters. So thank you for being here today. I'm not going to give like an in-depth overview of AFRL. I think everybody is fairly well familiar with AFRL, but instead just talk briefly about our small group. We're a group comprised of people interested in space technology, and for us, that means sensing either for space or from space. So as that relates to our grand challenge here today, is we're looking to kind of break through some of the traditional imaging constraints that are imposed on optical systems and look for novel solutions that are able to resolve features or details or provide information-related tasks beyond the Rayleigh resolution limit. So really kind of imposing some of those challenges. And, you know, at AFRL, as we're thinking about this grand challenge and the pitches that we're going to hear today, we're really trying to transition the research. So we always talk about things at AFRL in terms of 6.1 basic research and 6.2 applied research. And I really think that's where this technology resides today, is in that transition state. So as we look at our grand challenge problem, as it's applied to space debris detection and interstellar object characterization, we're really trying to take some of those basic research theories and algorithms and ideas that the three groups here have today and transition that into our applied technology area. And what we're really hoping to hear is how these ideas take some of the foundational theory and apply different noise sources and applied research constraints, practical limitations with hardware, and how that will relate to the different ideas and algorithms presented. So as you're presenting today, I hope you just keep that in mind. Really, we're all here and we're just excited to hear what you have to present us today, and just excited about this grand challenge in general. So thank you very much. And with that, I'll hand it back over to Caroline.
Thank you so much, Steve. All right, everyone. So I will briefly reiterate the run of show, and then we'll go ahead and get started. So SciCat, I believe your team is up first, so from the University of Arizona. And so how this is going to run is each team will have 10 minutes to publicly pitch, followed by 10 minutes of private Q&A, and then another 2 minutes of silent scoring by our review panel. So SciCat, if you would like to go ahead and share your screen, I will get my timer ready.
Sounds good. Are you ready?
Yes, and so I will raise my hand at the 1 minute mark for you.
Perfect. Sounds good. Good morning, everybody. I'm SciCat Guha. I'm a professor with background in quantum optics and information theory at the University of Arizona. Our team is led by Professor Amit Ashok, a computational imaging expert. My student, Michael Grace, is a DARPA Risers awardee who worked on quantum limited super resolution imaging the last 5 years. He's defending his PhD thesis this Friday and will be joining the Grand Challenge team if awarded as a scientist at Raytheon BBN. Professor Mark Neifeld is an adjunct professor at UFA, former DARPA PM. He'll be supporting us as an SME consultant. In the IAMBIC program, our team designed an algorithm to localize P emitters and estimate their brightnesses. Our algorithm iteratively picks the most informative parameter to estimate, some linear combination of the 3 P parameters among a collection of models where each is associated with a different estimate of P from a brief direct imaging pre-estimate. Then it detects a small integration time slice with the quantum optimal modal measurement for that parameter, updates the posteriors, and then repeats. In the breakthrough result mid-IAMBIC, we updated our optimal measurement choice from the SLD eigenvectors, which is a Fisherian construct, to the Bayesian counterpart developed by Stupersonic in 1973, which can employ the incrementally accumulated priors much more effectively. This led us to an algorithm that can resolve 4 to 6 point emitters with a 0.25 Rayleigh field of view with about 10 to 24 fewer photons compared to ideal focal plane imaging. We developed another modal algorithm to tell apart between objects from a predefined library, for example, barcodes, QR codes, or a human iris database. The probability of error of misidentification goes like e to the minus xi n, where n is the total mean photon number collected during the integration time. We showed that this xi, plotted on the y-axis here as a function of gamma, the spatial extent of the widest object in the library in Rayleigh units, goes as order gamma to the 4th for ideal focal plane imaging and as order gamma squared with the quantum optimal receiver. Interestingly, if the object library is precisely known, we showed that the quantum optimal performance can be achieved with a simple static 3-mode demultiplexer, a tri-spade, in the highly sub-Rayleigh regime as we showed in this paper. Even when gamma is not extremely sub-Rayleigh, the quantum optimal performance can be attained with a static spade, a spatial mode demultiplexer. In the presence of excess noise, for example, detector read noise, an adaptive spade outperforms the static spade for this problem and beats direct imaging, again by roughly a factor of 10 or so in the integration time. And we can discuss more details about this in the private Q&A. We found that the variance of the relative estimation error of the 2-point source separation problem and the exponent of the probability of error for the object classification problem have identical classical quantum gaps and scaling laws with respect to gamma. Now, any scene can be pieced together by the moments of its radiant exitance, while the variances of the first moment estimate for direct imaging and spade scale exactly the same way with respect to the object's length in the sub-Rayleigh region. There is a quadratic sensitivity gap in how the variances of the respective second moment estimate scale. Since the estimation sensitivities of the higher order moments diminish very rapidly, the higher fidelity second moment estimate of a spade really is the underlying driving force in the modal solutions for both detection and the estimation tasks. In a point calculation, we showed that estimating the length of a 7-meter geo satellite of magnitude 13.5 to, let's say, an RMS precision of about 7 centimeters can be achieved using a 30-centimeter telescope in about 5 minutes or so with a modal imaging solution versus 100 minutes with idealized direct imaging when using AO-corrected imaging, collecting photons in the visible band between, say, 450 to 650 nanometers. We have done an extensive calculation of the performance in broadband illumination with an optimized array of spades designed for discrete center wavelengths. The improvements over direct detection can be even more pronounced, exceeding about 100 times improvement with just 3 spades with optimized center wavelengths. We'll be happy to again discuss these results in more detail in the private Q&A. This slide shows our 3-stage proposed approach. We will focus on object detection, tracking, characterization, and classification in geostationary orbit. We will first begin with acquiring a full-wave spatial radiant exitance model of the scene via a prior acquisition phase from a combination of user-defined priors, for example, known object and known orbit, and direct imaging. This pre-estimate will include the star field background and potentially a catalog of known orbital objects, both in GEO and LEO, including their temporal periodicities, if any. In stage 1, we will use modal imaging for dynamic event detection at about a 10 to 20-fold smaller integration time compared to direct imaging. This stage will detect expected and unexpected flyby objects, breakage, change, and deviation from a known geo object of interest, for example. Our initial attempt will be to use the tri-spade second moment tracker for this stage. In stage 2, we will use a modification of our point source localization algorithm to sub-diffraction localize, track, and image a sparse scene after an event of interest happens. Finally, in stage 3, if mandated by the use case, we will classify among known and unknown objects. Our Iambic team has entered a tech transition evaluation phase to extension phase, where we are evaluating modal imaging solutions for multi-aperture telescopes, including a variety of real-life effects and non-idealities, which again, we are happy to discuss more in private Q&A. The execution of the grand challenge obviously will benefit immensely from this parallel effort. Here you see a hand-drawn cartoon of the stage 1 of our solution I just described. So the blue line here depicts a periodic yet known second moment of a known sub-Rayleigh geo object observed by, say, a ground telescope. Periodic, well, perhaps due to its gyroscopic precession. When an unexpected or an expected flyby event occurs, for example, stars or an unexpected space debris or an adversarial asset that flies by our field of view, but does not affect our object of interest, we will see blips like these in the second moment, which will come and go. Triggered by occurrences of an unexpected blip, our telescope could turn into stage 2 to track or image the unknown object of interest. Now, when a permanent change happens to our object of interest, the second moment will not return to the expected norm. At this point, our imager could turn into stage 2 or 3 to localize, image, or classify objects of interest after the detected event happens. In any of these cases, our spade-based second moment tracker will track the true second moment of the scene with a quadratically small variance compared with direct imaging. And this will result in detecting any change or deviation in the object or detect unexpected flyby or vital objects with about 10 to 50x lower integration time compared with a traditional direct imaging focal plane sensor. This stage 1 will be demonstrated in a proof of concept during a 9-month POP with a SLM-based mode sorter and a programmable scene generator. Now, our team has built this fully programmable mode sorter that works by passing the multimode light through successions of phase SLMs and free space Fresnel diffraction segments. This multi-plane light conversion, or an MPLC system, can sort arbitrary groups of co-propagating orthogonal modes with crosstalk of less than 0.5%. We programmed the MPLC to sort these 4 mutually orthogonal binary phase Hadamard modes into these 4 distinct spots on the active surface of our EMCCD sensor array. We programmed this MPLC mode sorter to realize a Hermite-Gauss binary spade, which in a proof of concept experiment shows 10 times reduction in RMSE in estimating the distance between 2 point sources at about a 0.1 Rayleigh separation. We will use this binary spade as the second moment tracker for the demonstration of our stage 1 design. For this grand challenge, we will also build a programmable scene generator to emulate the geo environment I just described, replete with a known geo object with its orbital precession, expected flybys occurring from the starfield background, unexpected flybys from space debris in LEO or MEO, for example, or from adversarial objects that are close to our geo asset. Our team has enjoyed a decade-long history of innovation on this topic. I presented our first result on a binary spade-assisted 1 versus 2 source detection at the single photon workshop at Oak Ridge in 2013. And this was funded on Mark Neifel's DARPA DSO Info program. In a DSO reveal program project led by Amit, we extended our work to arbitrary point spread functions and introduced the first adaptive modal imager that treated the unknown centroid as a nuisance parameter, which formed the backbone for algorithm that we are working with in our Iambic project. In a DSO extreme project that I led with Amit, Michael investigated mode sorter, crosstalk, and leakage. 2017, our arbitrary PSF work led to a DSO seedling with Joe, where we derived the quantum limits of resolution. I already told you about the Iambic work, and we have been extending our work to read noise, broadband illumination, partial coherence, arbitrary imaging space bandwidth limited scenes, and building mode sorter. And in a recently awarded phase 2 extension, we are developing modal imaging methods to support multi-aperture imagers, much like our AFRL FIS systems. So we are well poised to transition our innovations to transformative disruptions in the DoD missions, the Air Force, and the Space Force, well beyond the immediate scope of this space debris detection. So we look forward to the opportunity to tackle this grand challenge. And thank you for your attention.
With a few seconds to spare. Great job. Okay, so that concludes the public portion of this pitch. I am about to open the breakout room for the private Q&A. So I'm going to do that. If you do not automatically see it pop up, please let me know. So the room is open.
I don't see the rooms yet. Do I have to do anything, Caroline, on Zoom?
Okay, I'll move you into the room. Give me
Okay, got it. So I have Zach Dutton, Amit Ashok from my team.
As Caroline does that, if you're not part of our presenting teams today, you'll just stay in this room with us. And there will be a couple of presentations while team one answers questions.
Okay, I believe all of the panel and presenters have joined the room. If that is not the case, please let me know.
I have not yet been.
Oh, thank you, Neil. Okay, you should have just gotten the invitation.
Excellent, thank you.
Okay, all right. So without further ado, I would love to introduce our first speaker. Abigail Desjardins is the Venture Portfolio Director and Acting Director of Research here at Ensign. She has graciously agreed to give an overview of all the exciting work that Ensign does. And so without further ado, I will let Abby take it away and I will go join the breakout room.
Thanks, Caroline. Hopefully you guys can hear me. I apologize that I'm going to be off screen today and with some background noise. So please bear with me on this. Again, good morning. My name is Abigail Desjardins. As Caroline mentioned, I'm the Venture Portfolio Director at the National Security Innovation Network, or Ensign. We have a mission to build networks of innovators and problem solvers to generate new solutions to national security problems. Thanks, Allie. Leave that up there for 1 minute just so folks can read that. Okay, can we advance to the next slide? Ensign is an office within the Department of Defense Research and Engineering. It became a DoD program of record in FY20, and we deliver programming and services to problem owners within the Department of Defense and the Fourth Estate. Next slide. All of our activities at Ensign are focused on tapping into communities of problem solvers who have typically been out of reach by the department. And this is based on the fundamental belief that we're in a complex, rapidly advancing world, and the rate of change and innovation within the Department of Defense is not keeping pace with our adversaries. We believe that if we, the Department of Defense, want to maintain resilience, leverage emerging technologies, and solve problems differently, then we need to incorporate new problem solvers. We recognize that there exists amazing talent and technology within our universities and our communities, both inside the Beltway and far outside the Beltway. And we should make a much more deliberate effort to identify, assess, and accelerate access to those viable, feasible, and desirable solutions, and the talent behind those solutions. For those of you unfamiliar with Ensign, we have two distinct but intertwined functions. We have the regional network team and the program team. The R&T is geographically spread across the United States, leveraging a hub and spoke model. The 9 hubs identified as regional centers of gravity are staffed with a regional director who is responsible for understanding and developing the regional ecosystem. The spokes are staffed by a team of reps, regional engagement principals, who are focused on bringing Ensign programming to the local ecosystem. Next slide. On the program side, Ensign offers 2 lines of programming via a portfolio structure. Our programs are built to provide support to the services and OSD for any problem across an incredibly broad spectrum, from the hyper-tactical to policy and beyond. The 2 portfolio programs we offer are the talent and the venture. The talent programs focus exclusively on the individuals and the entrepreneurs as inputs into the programs, whereas the venture portfolio is focused on ventures. Next slide. In the last 6 years, we've had tremendous success in bringing DoD problems to non-traditional problem solvers. The numbers here are a snapshot of our impact. As of today, we have brought in just over 1,300 early stage ventures into the National Security Innovation Base and engaged with another several hundred known vendors in the NSIB. The companies who have participated in our programming, like today, have gone on to secure just under $3 billion in DoD funding post-program and just over $9 billion in private capital post-program. Next slide. Next slide. One of the services we offer at Ensign resides within enterprise services, and that is the support from the transition cell. The journey of our alumni companies of supporting the United States government has just begun, and some are not quite ready to navigate the journey on their own. Our team of subject matter experts is available to support program participants, providing critical feedback and our support to them. You will hear from this team in just a few minutes with more details. Again, I thank you all for being here today, providing your time and expertise in support of AFRL. We cannot maintain our competitive advantage without you. Please reach out if you have any questions or would like more information about Ensign. And thank you very much. You know, Ali, I just realized I spoke a little fast. So we have about 6 minutes before the panel of judges reconvenes. So if there are any questions from the audience, I'm happy to take them at this time, or just give people some time to have some additional cups of coffee.
If anyone has questions, you can, oh, there you go, you're on. Good, thank you.
Yes, I'm Alexei Gon, I'm with Princeton University. So what's the difference between NSIN and other agencies like DARPA? You know, there are many agencies. So what differentiates you from the rest?
That's a great question, one that we get a lot. There are a ton of other innovation organizations. One of the things that makes Ensign very unique is that we are a joint organization, meaning that we represent the entire United States government. We also do not focus on basic research or advanced research or a set grouping of technology vertical areas. We really work with duty mission partners who have problems that align to our programmatic execution needs. So meaning, you know, if they have a problem that aligns to meeting a dual use accelerator or a pitch competition, and then we will execute programming on their behalf. We also, as a government organization, do not provide investment in companies to further the state. We do that through other means, but we as ourselves do not do that. Any other questions out there? All right, well, thank you again for being here today. And I would say take this time, the last few minutes before the judges reconvene to jot up some emails or get another cup of coffee. Thank you.
Hey everyone, welcome back. It looks like our panelists are returning. Thank you everyone for your time and attention. Hopefully Abby's talk was interesting and you had a nice little break in there, but it is time to keep the show moving along. So our next team is from the University of Central Florida. So they will be presenting their pitch solution. Stephen, are you ready? Are you the one to be presenting, correct?
Yes, yeah, I'll be presenting.
Okay, great. So once your slides are up, I will begin the 10-minute timer and I will raise my hand at the 1 minute mark. All right, here we go.
Okay. I'm Steve Eikenberry from the University of Central Florida's College of Optics and Photonics, CREOL, and I'm here to tell you about our photonic quantum-inspired imager PQI2. Our team, by way of background, I'm primarily an astrophysicist. I've spent the last 25 years leading major astronomical instruments for the world's biggest telescopes, including the Gran Telescopio Canadia's 10.4 meter, the Palomar 200-inch, and various others, including diffraction-limited imagers and spectrographs among these. We also have Rodrigo Amezcua Correa. He has spent 20 plus years leading fiber optic device development micro devices, also MPLC work for wavefront engineering. He leads our fiber optics research center here at the University of Central Florida. It's the leading facility of its kind at any North American university. He's also the top U.S. manufacturer of advanced photonic lanterns that we'll talk about in a moment. We're joined by Major Matt Cooper, who is on special assignment from the U.S. Space Force to do his PhD research with us here at Creel, and Professor Carrie Donaldson-Hanna, who's an expert in spectroscopy of asteroids, moons, and airless bodies, PI of an upcoming lunar rover mission. We also have a number of PhD students, postdoctoral fellows, and research scientists here. And we brought this team together to address space debris, the fact that there are 100 million pieces of space debris in orbit around the Earth, and even pieces the size of a marble, 1 centimeter, can disable a major satellite. Now, scattered sunlight gives us a lot of photons off of these things. Unfortunately, though, those pristine wavefronts have to propagate through the atmosphere to get to our telescopes on the ground. The atmosphere introduces a large number of phase aberrations. So we get an aberrated wavefront that our telescope collects and puts that into a blurred image that is then sent to an adaptive optics instrument or an adaptive optics system, a very complex, fairly expensive piece of hardware that will then try to put all that light back together into a diffraction limited image. Even if it's successful, though, that's 10 times bigger than the 1 centimeter scale that we're trying to image up at LEO. So the question is, how do we overcome this? That's the motivation for this grand challenge, is quantum inspired imaging. The idea, again, is that we take this blurred image, it's instantaneously blurred at any second or any millisecond, it looks like this. It moves over through adaptive optics to get to the diffraction limited image here, ideally. And then we pass it to a spatial mode sorter, and that separates out the phase and amplitude of each mode. And then we can take that information and reconstruct it through algorithms to produce a image space source function that is 10 times sharper than the original diffraction limited image. Now, our approach is slightly different from this, and that's because it's based on the recognition that adaptive optics systems actually take this initial incident image at a short wavelength. From that, they measure the phase aberrations due to the atmosphere. They apply them at longer wavelengths using a deformable mirror to correct them and bring all those little modes back together in phase. So we have a nice diffraction limited image that then we pass to a spatial mode sorter that takes them all apart again right away. So rather than going through that expensive and complex loop, we actually bypass adaptive optics entirely. We take our incident image, but now broadband, going from 400 nanometers out into the near infrared. So we have a huge grasp of information. We have all the photons and all the information provided from the object. We pass that to a spatial spectral mode sorter, which is a device we actually happen to have here. And that allows us to measure amplitude and phase of each mode as a function of wavelength. So not only do we get the image space source function reconstructed here at high resolution and at higher signal to noise because we have many more photons to grasp, but also we get the wavelength response of each component of the debris, and that gives us spectral signatures that can differentiate between different kinds of debris based on their composition. So our background on this, we were coming from advanced photonic technology in the telecoms industry, photonic lanterns, MPLCs, and such like, combining those with high resolution astronomical imaging to produce PQI2. We'll go into the details in a second here, but just to highlight the key performance advantages, PQI2 will reach the subdiffraction limited imaging that we need to resolve the space debris. It has high throughput, both in terms of the optical efficiency, but also just the grasp of having all the photons from 400 nanometers out to the near infrared. It's low cost, simple. It has no adaptive optics, so that allows us to deploy it cheaply, opening up the possibility of multiple facilities to study the large population of space debris in orbit. It also does not suffer from the residuals of adaptive optics. Even systems like EOS will only put about 15 to 20% of their light into that diffraction limited point spread function. The rest of the light tries but doesn't make it there. So most of that light is left lingering around in systematic deviations, producing things like super speckle that are extremely hard to distinguish from the underlying source function that we want to detect, especially if you've got a relatively narrow bandpass. We are broadband, so we can get the target composition, and we are low swap for many future applications. So our fundamental overview of PQI2 is, again, space debris illuminated by the sun. Wavefront is aberrated by the atmosphere. The focus collects that light, or the telescope collects that light, focuses it down onto the focal plane. We beam split between two photonic lanterns, spatial mode and multiplexers that I'll talk about in a second. The outputs of those are each single mode optical fibers that we can then disperse and therefore project that onto our detector and get that amplitude, phase, and wavelength dependence of all of our modes. There are three critical innovations on this: the photonic lantern spatial mode multiplexers, the atmospheric blur removal that is enabled by their spectral and spatial diversity, and then the machine learning quantum inspired imaging algorithms for reconstruction. All these innovations are based on proven technical solutions. So our photonic lanterns are fundamentally fiber optic devices that take a complex input beam and in hardware, in analog, decompose those and sort them into an array of single mode fiber output ports. So you can see here in the lower left, we've got a little animation of different wavefronts coming in. It goes through a transfer matrix we can see there in the middle. And then the intensity, the weight that we get out of each mode tells us how we could recompose things to recreate that wavefront. And again, the more complex the input beam, the more modes we need, but it will work at great, very high complexities. We've built a large number of these devices. This just shows an example. They're custom designed, so we design the modal base to match the application at hand. It's kind of like an ASIC in optics. You know, it's a hardware fixed device that provides you optimal performance. We've fabricated these devices. You can see the devices here in the middle on a optical bench, 1/4-20 holes at a 1-inch pitch. The fabricated devices, once we package them, are about the size of a ballpoint pen. Here's one right there. You can see it. They have very high efficiency, greater than 98% optical throughput. And we've used these for telecommunications, wavefront sensing, free space communications, et cetera. And we have a demonstrated track record of delivering custom mode sorters. Then the next innovation, again, is the atmospheric turbulence correction. And what I'm showing here in the top left is a phase map of the errors that the atmosphere produces at 550 nanometers projected onto a telescope pupil plane. The one next to it is the same exact thing at 1100 nanometers, and you can see the shapes are the same. Okay, the shapes are fundamentally the same. The amplitudes of phase are very different because those depend on the index of refraction of air, which is wavelength dependent. But we know that dependence. And so each one of those wavelength channels actually gives us an independent estimate of all the phase errors. And so with many wavelength channels, we get a very precise measurement of the phase errors in the atmosphere, and we can remove those. At the same time, we've still got the modal information we can use for the quantum inspired imaging. That's limited by diffraction, which has a completely different wavelength dependence. There, the resolution goes as lambda over the diameter of the telescope. So longer wavelengths have broader PSFs. And again, using the fact that these are very different wavelength dependencies, we can break the degeneracy between these effects. And at the same time, using our broad grasp of photons, maximize the signal to noise ratio. Our image reconstruction path goes here. I won't, due to lack of time, I won't go into too much detail, just to point out that once we have the source function reconstructed at all those wavelengths, they, of course, are not completely separate from each other. Different wavelength channels next to each other should share the same underlying distribution of objects and so on. So we use reinforcement machine learning to try to piece those together into a 3D data cube of source functions where it's intensity versus X, Y, and the Z direction on that cube is wavelength. Then our simulation shown here, we have a 1-inch piece, another 1-inch piece, 2 inches apart at 300 kilometers. We get a signal to noise of about 5 per exposure per channel per mode. If we take then our data cube and squish it down in wavelength so that we're only looking at intensity, you can clearly see the 2 blobs here, well separated. At the same time, we can drill through each of those blobs in wavelength space and get the underlying spectral response. And you can see that artificial satellites look very different than the olivine absorption feature you get from an asteroid fragment. So, and our resolution floor is well below the 1 centimeter requirement that we set here. And our project plan, this basically follows along the plan set by the Grand Challenge for us. It's a 9-month plan to get us on sky and taking images through the atmosphere in anger and getting to the resolutions that we need. Thank you very much.
Thank you so much, Stephen. So that concludes the public portion of this pitch. I will go ahead and open up the breakout rooms. I will have to manually assign again, so please bear with me. In the meantime, we do have another round of speakers for you. The Ensign Transition Cell with Toby Armour and John Ribnack is here to present about what the transition cell services at Ensign offer for Ensign alumni teams and startups. So as I assigned the breakouts, Allie's going to bring up the slides for them.
Yeah, sounds good. We also have Chris Fodiatis, who I think is getting ready to jump into one of the breakout rooms, but also on the transition cell.
And we're still waiting for the breakout room invitations, I believe.
Yes, I am sending those now.
Okay, John, you're all set.
All set? Awesome, thank you. Yeah, well, it's a pleasure to be here. Thanks for having me. Myself, Toby, and Chris are on a team within Ensign called the Transition Cell. Abby earlier talked briefly about our team and what we do, but I'll dive in a little bit deeper and then happy to answer any questions. So our role within Ensign is to work across our regional teams and to work across our program managers to one, support them in the programs that they are running, and then also support teams and companies such as yourselves as you are participating in and graduating from Ensign programs to continue helping you along your growth and trajectory and acceleration, and ideally help you transition solutions that you are developing to the DoD. So we do that in a number of different ways. I focus on private capital and helping companies understand what are the milestones and goals that they want to achieve over, say, the next 18 to 24 months. What are the resources that they need to acquire in order to achieve those goals and resources? And then what is the capital that they need to raise in order to acquire those resources? So going through this very targeted capital access planning process. And then also on the other side of that, really working to build out our network of investors, understanding who are the investors in our network that are focused within specific sectors at specific stages, and also have some level of focus on defense technologies or dual use technologies. And then if and when there is a fit, making introductions between those companies and those investors in hopes that eventually that will lead to you as a company or a team raising the capital that you need in order to accomplish your goals and milestones. We also have Chris Fodiatis on our team who just moved into a breakout room. He's a prior contracting officer. His role is really to similarly step in with companies, help them think through what is their growth plan, delivering solutions to Department of Defense contractors or Department of Defense customers, and what are the contracts and opportunities that they can submit proposals against and try to win in order to continue growing their business with those DoD customers. So understanding what is their roadmap for growth within DoD, and then how do they go about navigating those different and various contracting pathways to continue growing. So most of our time is spent really working one-on-one with companies, understanding their needs and challenges, and then figuring out what is the next resource that we can connect them to, and the next level of support that we can provide to continue helping them along their paths. And that's where Toby really steps in to help us as a team understand what are those needs and challenges and gaps for those teams and companies, and how can we continue supporting them. So this slide in particular, somewhat outdated. I think we've worked with close to 100 companies coming out of Ensign programs at this point, and that continues to grow every week. So hopefully coming out of this challenge, a few of you will reach out to support from us, and happy to schedule some one-on-one calls to think through what are the things that we can do to support. Just as a couple of examples, so I've worked with a few companies to think through say, valuations as they're trying to raise a pre-seed or a seed stage financing, or to help them better understand, if they've received a term sheet, what are the things that they should be thinking about. What are some of the potential pitfalls in a term sheet that might negatively impact their business or governance or equity, all of those types of things. We're just generally helping them, again, think through their capital access plans. Chris has helped companies think through, what are some relevant, and Toby as well, what are relevant contracting opportunities they should be looking at, helping them think through, not writing a proposal for a company, but helping them understand and assess whether the proposal that they've written is hitting all of the things that it needs to hit in order to be positioned for success when they submit it. So we really try to dive in pretty deep with customers or with teams and companies. We'll usually have, several phone calls with each of those teams and companies over time to really make sure that we understand what it is they're trying to accomplish and how we can best position them for success. So I think that that's a pretty good overview. Toby, anything that you would add that I missed?
No, John, I think you pretty much hit everything there.
Cool. Well, happy to open it up to any questions for us. Awesome. I love it when
what's
I
the,
answer everybody's question. There we go. All right.
So what's the typical size of the company? When it starts, it's usually husband and wife in the kitchen, right? So, or do you need to have already established business some sort?
Yeah, so I think our team can be most effective when there is a business entity established. There's a team supporting, the business. Ideally, that they're working on the company full time, but at least part time. Then I think we can provide a little bit more value in the type of support and consulting that we're doing with those companies. But we're still happy to connect with a team, even if a business entity hasn't been formed yet around a technology. I mean, as far as stage, though, it varies depending on the programs that we're running, who the DoD customers are that are affiliated with those programs. I'd say, we're typically looking at companies where, there is a business entity established. They have at least a prototype developed and a couple customers that they've interacted with, and there's some level of customer validation or customer discovery that's happened. And there's some plan in place from that company for where they want to go next, right? So thinking in terms of investment round, we're, I think, for the most part, looking at pre-seed to seed stage companies, TRL, 4 to 6-ish. And so really it's those companies where they've got something that they can point to, a technology or solution that they can point to or demonstrate, and they've got some level of customer validation, and we can really help them think through what are next steps in their development life cycle. Alexi, did that answer your question?
Yes, just I work for Princeton University, so there is always a little bit of, I work for university, your IP belongs to university. So then, if you start a company, it's difficult to keep your IP while working at the university at the same time. You will have to either license it out of university and so on. It's a little bit of conundrum.
Yeah, yeah, agreed. Happy to schedule a call sometime if you want to talk more about that.
Sure. Yeah, I think I sent you a LinkedIn request, so we can chat about it later.
Sounds good.
All right, great.
Any other questions? All right. Allie, Caroline, I'll turn it back over to you.
Thanks, John. We have about another 7 minutes before team number 2 will be back in the meeting. So Everyone just take a quick break and we'll be right back.
Welcome back, everyone. I believe everyone from the review team is back in the main room. So we have one more presentation for you all. Zubin will be presenting from Purdue University on their proposal. So Zubin, you'll have 10 minutes. At the 1 minute mark, I will raise my hand. It looks like you're already all set up. So without further ado, you can go ahead and get started.
Great. Thanks, Caroline. Before I get started, can you hear me? Can you see my screen? And can you also see my pointer?
Yes, we can.
Okay, excellent. So I'll get started on my stopwatch over here and welcome everyone. My name is Zubin Jacob. I'm from Purdue University. Thank you for coming to my talk. Thanks to definitely the judges for giving me the opportunity, and also congratulations to all the finalists for this really exciting AFRL Grand Challenge pitch. So we'll be talking about the adaptive quantum accelerated imaging for space situational awareness. Now, as part of the AFRL Grand Challenge, what we want to do is actually push the frontiers of imaging in the visible and infrared using kind of the type of telescopes that we use right now. So we want to be looking at the photon starved regime as well as the sub-Rayleigh limit, where the conventional approaches that you can see over here, they actually have a universal theme of errors in estimation. So if you look at the wide variety of tasks that will be of interest for space situational awareness, all the way from, say, centroid estimation or object classification to things such as light curve inversion, where you have subtle changes in brightness that can give you insights on maneuverability or angular momentum of the object. In all of these cases, the conventional Rayleigh limit does pose a challenge, right? So our approach is to adaptively optimize the task-specific information theoretic metric per photon. And as I mentioned over here, this is just results of extensive benchmarking that we have done using various techniques to show that the direct imaging in this low photon number regime has a lot of errors. So this is work we accomplished through the DARPA IAMBIC program. This is in this paper right here. You have a scene, there's a pupil plane, and you do the conventional direct imaging on this imaging plane. Now, through this set of kind of benchmarking that we have performed, we came up with a direct imaging method that outperforms like Richardson-Lucy and Clean, as well as the Gaussian mixture model. And in the low photon number limit, what you're kind of seeing is that the ground truth position is not estimated properly by this approach. However, if you consider a different method, which in the community is known as this mode sorting, you can have the imaging plane in which you can adaptively sort the modes in the different spatial modes and actually then perform your imaging. So right here shows a movie of the various modes that are predicted by the algorithm. This is the spatial profile. There are 13 iterations and there are 3 modes, and you can see that the estimation error decreases. And this is not an isolated result. Since April 2021, we have run this on 10,000 cases and shown this is indeed robust. But to take something from a theoretical construct to actually a field demo is a completely different beast. There are a lot of challenges in mode sorting and mode projections, which I've outlined over here. Let's try to look at it qualitatively and give you a quantitative insight very soon. So first is system level photon efficiency. For every single photon that enters your aperture, it is carrying information. So you really want to be able to detect that. Now, if you look at direct imaging, your advantage over direct imaging will be lost if there's any decrease in system level photon efficiency. The same thing, another important thing is adaptivity. Since you have no prior information, you really want to be looking at a very wide set of modes for wide-ranging tasks. And there are lots of system-level non-idealities, including detector noise, modal crosstalk, timing jitter, amplitude noise, that needs to be considered. And even if you actually overcome all 3 challenges, then there are 2 more. One is atmospheric turbulence, which is spatio-temporally varying kind of wavefront distortions. And the other one is actually the very significant one, is that there are millions of dollars investment already in existing adaptive optics. Global adoption of kind of any technology that we come up with requires at least being able to compete or outperform existing adaptive optics. So we believe we have overcome this intertwined challenges through a paradigm shift in approach. We do not use mode sorting or mode projections at all. So this is our new architecture. We call it adaptive Fisher interferometry. for every single photon that enters the telescope aperture, we have optimized our system right now at 532 nanometers. So that's what this bandpass filter is. Every single photon comes in at this polarizing beam splitter. It actually has two pathways that it can take. Now we've optimized the spatial light modulators at the single photon level such that these two pathways have different single photon modulations, and then they interfere on this beam splitter. And after that, once again, it can take two pathways, and then we measure it on single photon detector arrays. And this is what we call as adaptive Fisher interferometry. Over here is what the GPU does. These are the different aspects of the single photon modulations as well as the single photon distributions on this arrays that is actually controlled through the GPU. And this is really unique custom built hardware. Now, the most important thing I want to mention is the architecture for every single photon, even with low cost SPAD arrays, can give you 25%, which is 10x better than existing architecture. And if you're willing to invest higher, you can go up to 75%. For every single photon that enters, there's 75% probability that it will reach either this SPAD array or that SPAD array as a click. The modal complexity is over 10⁶, and there are other details that I'll come to very soon. This shows kind of the important result that we've recently achieved, which shows the entire kind of pipeline, including the single photon modulations as well as the single photon distributions and comparison to mode sorting. So a very important thing is that once you add non-idealities into mode sorting, the AFI actually outperforms or at least performs as well as the mode sorting in the idealistic regime that we have been looking at for a long time. And once again, this is not an isolated result. We have extensive non-idealities included with over 1,500 cases where continuous brightnesses and continuous ground star locations have been taken into account to actually look at does our technique outperform, and we strongly believe that is indeed the case. Again, but this is far from kind of where we want to be, because there are two big challenges remaining. One is atmospheric turbulence, and the other is, can AFI compete and possibly outperform existing AO architecture? So let's look at this existing AO pipeline. The first and most important ingredient is actually this wavefront sensor. But if you look at Keck or look at any of the telescopes, one of the key things is that as the magnitude of the star decreases, you enter this low photon number regime, and the wavefront errors increase exponentially. And this is a universal theme. We believe this is exactly the regime where adaptive Fisher interferometry can compete and possibly outperform this set of conventional AO. So this is the key new approach. We call it de-aberrative single photon modulations. For the experts in the audience, I should mention that we extract information from every single turbulent photon entering the aperture. We have no wavefront sensor, no deformable mirror, no computational imaging techniques like Gertzberg-Saxton algorithms, and we have no guide star. What we do have is photonic information theory, the adaptive Fisher interferometry, as well as the Kolmogorov theory of turbulence that we have built in a way such that for every single turbulent photon entering the aperture, we apply de-aberrative single photon modulations, and then we can show that adaptive Fisher interferometry actually can compete with the existing Strail ratio of 0.7 in existing adaptive optics systems. This is what the GPU kind of processes inside. These are the kind of four main ingredients that the GPU processes. This is the turbulent point spread function, and this is kind of what we have in the estimate. And this is actually clearly better. We believe we can show this in a 5-month time frame. So what will we do? We hope to actually run a lab demo within 5 months so that the AFRL kind of team can visit Purdue over here. This is what you see is the extensive kind of SNR as well as the integration times that you have. This is the source, kind of weak source LED. We have fabricated test objects with lambda square area. We will have a home-built turbulence simulator. And then through this AFI, we expect to extract for multiple cases the centroid, the number of objects, the brightness, as well as image reconstruction with and without turbulence. So the magnitude that we want to hit is actually 14.5. That's the star magnitude. The photon flux that will enter the aperture. Sorry, is there a question? If not, I'll continue. The photon flux in the aperture is 368,347 photons per second for a 0.61 aperture. For every pixel in our AFI, we expect 8.7 photons to hit it. And the total number of pixels that are illuminated will be 50. And this gives us the limiting SNR of 1.4. And that's kind of the entire system. And just looking ahead, when you come for the lab demo, we believe we can show you the turbulence tracker. On the left-hand side is kind of the turbulence phase, which is changing. And on the right-hand side is the retrieved phase that we believe we can show in real time. Our technique is also applies to actually extended objects. And that's kind of an important point that I want to mention. So with that, I want to talk about our team and capabilities. We've already established a lot of software tools through the IAMBIC program and collaborations with Vaneet Agarwal. We've also had a lot of history in super resolution imaging that I've mentioned over here, but I want to draw your attention to kind of the lab experiments that we perform on a daily basis. This is with 6 millisecond integration time. This is actually, you can see the axis over here. It's almost in the few photon regime. It's only 40 photons per pixel, and the SNR is 20. Now, as part of this AFRL approach, we want to actually peak inside this each sub-diffraction low photon number regime. And this is exactly at the wavelength where our system is optimized, which is at 532 nanometers. So with that, I want to conclude my talk. Thank the audience for your attention. And this is the summary of the fact that there are 5 intertwined challenges that we believe adaptive Fisher interferometry can solve. And when you come for the Purdue lab visit in month 5, we hope to be able to show you experiments with a star magnitude of 14.5, an SNR of 1.4, and an exposure time and integration time of 10 milliseconds. The isoplanatic angle, Fried parameter, atmospheric turbulence time, I didn't get time to talk about it, but I'll be happy to answer those things in more detail during the Q&A session. With that, thanks once again, and I'll be happy to answer questions.
Thank you so much, Zubin. So that concludes the public part of this presentation. And so I'm going to go ahead and open up the breakout rooms for the 10-minute Q&A. And then when we come back, I'll briefly conclude, and then we'll resume around 1:30-ish for the finalist announcement. So with no further ado, I will go ahead and assign the breakout rooms. Please bear with me while I do so.
And while Caroline's doing that, we do not have a speaker during this break. So we will pause for the 10-minute Q&A and then the 2-minute judges deliberation, and we'll reconvene at 12:30 for final remarks before we go into judges deliberations.
So it is the end of the presentations and the Q&A. So I want to thank everyone for your time today. Thank you to the semifinalist teams. Congratulations on incredible solutions and fantastic pitches. I've certainly learned a lot and had a lot of fun listening to your work. Please do stay in touch. If you have not already, please make sure to visit the Ensign website, sign up for our newsletter. Ali is our director of communications. So if you have any questions about that, put them in the chat. Happy to answer them. Thank you again for all of your time. We will be announcing the finalist, so the winner of this competition, on this same Zoom link. So final deliberations will last until about 1:30. So if you want to just come back and check in around then, we will be making that announcement. So thank you again for your time today. Please do stay in touch and come back around 1:30 for the finalist announcement. Hello, welcome back, everyone. So the review panel, we have finished the deliberations. So I want to start off just by saying thank you to all of the teams who presented today. Thank you for your hard work that you put into those proposals. I very much enjoyed, and I know the review panel enjoyed hearing your proposals today. And we do have to select a winner. And so there was one team today that really stood out for their sound technical proposal, their high quality pitch, and their review panel really believes that they're a strong team with an innovative approach that has the potential to leap ahead in capability in the area of space imaging. And so for those reasons, the winner of this grand challenge is the University of Central Florida. Congratulations. Very excited for all of the teams. Please be on the lookout for an email from me with follow-on engagements with Ensign and the panel. But UCF, Stephen, congratulations.
Thank you very much. We're
Thank you
very
very
excited
much.
and looking forward to working with you. So thanks again.
Is that all, or
And we're just wait for context there. So we also enjoyed this. I will say, watching the other teams too, and seeing the cool things they're doing as well. Yeah, and we're very excited to move forward with this.
Thank you so much. Please look out for a follow-up email with us for next steps. That goes for all teams who participated today. So thank you again and congratulations.
Thank
Thanks
you.
all.
It was great.
All right. Bye-bye now.